Hello everybody, welcome to the next lecture. So guys, in this lecture, we are going to basically talk about another scenario where, let's say, our training data set has got two continuous valued features and one target feature column. Okay, so here you can see that very soon we are going to show you a scatter plot, and on this scatter plot we will be having two axes. One is our x-axis, which is going to be the feature x1 axis, and one is our y-axis, which is going to be our feature x2 axis. Okay, now let's take our training data and plot all the data points on this plot, okay, of benign as well as malignant tumors. So guys, you can clearly see that here we have plotted our training data, where each data point, suppose this data point, corresponds to some value of x1 feature on x-axis and x2 feature on y-axis. Okay, and the color of the data points actually tells us that whether this data point belongs to benign category or malignant category. Okay, now guys, if we see here, then the dimensionality of our features have increased. In the last scenario, there was only one feature column, that is feature X. But guys, in this scenario, we have two feature columns, feature X1 and feature X2. So guys, accordingly, our Gaussian likelihoods will also change for the case of malignant tumors and for the case of benign tumors. Okay, so guys, in this case, our Gaussian likelihoods are going to be basically PDF of two-dimensional Gaussian distribution. Okay, so guys, you know, and you have already seen that how a two-dimensional Gaussian distribution looks like. Okay, it's a kind of a mountain in 3D. Okay, but guys, if we are going to look up to that mountain, or we are going to have a top level view of that mountain, then it is going to look like a contour plot. Okay, so I'm here going to create a contour plot, guys. Okay, so reducing radius of the different contours indicates that we are approaching more height. Okay, so guys, in 2D, we are looking at this mountain and it looks like a contour plot. Okay. Similarly, for the benign scenario, the likelihood will again be a two-dimensional Gaussian distribution likelihood. Okay. And this again is going to be a contour plot. Okay, so guys, here we are getting basically two bivariate Gaussian distributions, and these two are our likelihoods. And guys, as you can again see that the two Gaussian distributions are actually overlapping with each other here. Okay, can you see the overlapping area? So guys, the scenario is exactly the same as in the case of only one feature X, where the two Gaussian likelihoods were overlapping with each other, or the two Gaussian distributions were overlapping with each other. Okay, here also the two mountains are overlapping with each other. And we are looking at these mountains right now in 2D because we can't look at them in 3D right now. Okay, but they are actually mountains in 3D. Now guys, similar to the scenario of only one feature, you can clearly see that these two Gaussian distributions will actually result in a sigmoid function. Okay, and this is the graph of our sigmoid function. Guys, let me make it very clear for you that this graph of sigmoid function is not in the x1, x2 plane. Okay, it's in 3D. The graph looks as if it is in 2D, but guys, this graph is not plotted in 2D, it's in 3D actually. Okay. And one more interesting observation, which you have seen from the previous scenario of one feature, that where the two distributions overlap with each other, there the sigmoid function is making transition from lower to higher height. Same thing is happening here also. So guys, you can clearly see that this is our overlapping region. And in this overlapping region only, the sigmoid function is making the transition from lower height to higher height. And this is where the probability of any data point line inside the intersection region or the common region or the overlapping region for both the scenarios of benign and malignant will be 50%. The posterior probabilities will be same and the classifier will get confused. And guys, it is the same region, the overlapping region, from where our decision boundary will also pass. Exactly the same scenario, guys. But guys, here you can clearly see one major difference, that the decision boundary is not parallel to y-axis. Why? Because guys, this time the equation of the decision boundary will not be in the form of x equal to something, because we have two feature columns here or two features here. So that's not possible in this case. And that is why, guys, it's looking like a diagonal line. And you can clearly see that it's passing through the same overlapping region where the sigmoid is making the transition from lower height to higher height, just like the previous scenario. That's interesting, guys. So there are so many similarities, except for the major difference that now the likelihoods will be two-dimensional Gaussian distributions. So the type of the distribution is also same, but the dimensionality has increased from 1 dimension to 2 dimension. Okay, that's amazing, guys. Now, guys, if suppose there are two such data points which are lying on this decision boundary, then what is going to happen with them? Well, guys, for those two data points, naive-Bayes classifier will not be able to perform proper classification, because for these two data points, the posterior probability of them belonging to benign as well as malignant categories will be exactly 50%. Okay, so that is the confusion state. In fact, any data point lying on this decision boundary, no matter whether it lies here, 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 anywhere, the classifier will not be able to perform classification, because posterior probabilities will be same, equal to 50%. Now, guys, let's talk about the major question, that what will be the equation of this decision boundary? Well, it looks like a difficult question, but guys, that's a very easy question. You know how we are going to get the equation of the decision boundary, and you know this equation where we took the ratio of two posteriors. And guys, we know this result, that if the data set is balanced, then the priors will get cancelled out. And for a specific tumor data point, normalizing probabilities will be same. And when you take the ratio, normalizing probabilities will get cancelled, and we will be only left with the ratio of the likelihoods. And guys, here you can see that we have used the PDF of two-dimensional Gaussian distribution. Now, guys, there are some differences when it comes to parameters of one-dimensional Gaussian distribution and two or more than two-dimensional Gaussian distribution. The difference is that in one-dimensional Gaussian distribution, we have variance. But guys, in two-dimensional Gaussian distribution or more than two-dimensional Gaussian distribution, we have covariance matrix. So guys, this is what we have, covariance matrix. Okay, covariance matrix for all the data points belonging to malignant category out of our training data. Okay. Similarly, here we have covariance matrix for all the data points belonging to benign category out of our training data. And guys, here you can see the two mean vectors. So mu hat x1m is actually computed from all the data points belonging to malignant category out of our training data, and that too for the feature x1. And this is computed for the feature x2, and they both are means. Okay. Similarly, guys, mu b x1 hat is actually mean of all the values belonging to feature x1 of all the data points belonging to benign category out of our training data. Similar is the scenario with mu hat b x2. Okay. And guys, these are the two values for our specific random tumor data point selected from cross-validation data or testing data for which you want to compute the likelihood. Okay. Now, guys, we are going to take the same assumption which we took before when our distribution was single dimensional Gaussian distribution or one dimensional Gaussian distribution. Then we took this assumption that we are going to make the two variances equal or nearly equal, which is equal to pooled variance. But here, guys, unfortunately, we don't have variance, we have covariance matrices. So that is what we are doing here. We are making both covariance matrices almost equal to something called pooled covariance matrix. And guys, when we apply this assumption, then these two terms will get cancelled and we'll be left with only exponential terms or exponent terms. Okay. And when we simplify them, okay, and we solve this whole equation of ratios, we get to know, guys, that equation of this decision boundary is going to be this equation. That is theta 0 hat plus theta 1 hat x1 plus theta 2 hat x2 equal to 0. So guys, theta hat 0, theta hat 1 and theta hat 2, you guys already know that what these things will be, because when you solve this whole ratio and simplify this equation, these theta 0, theta hat 0, theta hat 1, theta hat 2 will actually consist of some complicated functions of mu hat x1m, mu hat x2m, mu hat x1b, mu hat x2b, as well as covariance matrices. That means the parameters of your two-dimensional Gaussian distributions. So guys, actually, we know these constants. They are known to us. Okay, and we have taken here x1 and x2 as variables. Okay, and guys, this is the equation of our decision boundary. This decision boundary. Okay, and guys, you know that the equation of the decision boundary is actually what? It's simply discriminant function equal to 0. So guys, it means that this is our discriminant function. So if you want to perform classification, you can also perform classification using this discriminant function, because theta hat 0, theta hat 1 and theta hat 2 are already known to us. And you can select a random point. Let's say we have selected this random point. We get the value of x2 feature for this point, x1 feature for this point, plug in the x1 feature value here, x2 feature value here. And guys, if the discriminant score comes out to be, let's say, negative, then we'll say that the tumor either belongs to the benign category or malignant category, whatever. Because guys, in this case, it is very hard to say that if the discriminant score will become negative, then we'll say it's benign, or if it's positive, then we'll say it's malignant. It's very difficult, guys. In this case, we cannot be 100% sure. We have to see actually. Okay. But definitely, because this point, this point, this point, these points are not lying on the decision boundary, and therefore, guys, the discriminant score is never going to be 0, because they are not going to satisfy the equation of the decision boundary. So either the discriminant score will be negative or the discriminant score will be positive, and based on that, we can easily perform the classification of the data points from the cross-validation data or from the testing data. Okay. So guys, we have already now get to know that what will be the discriminant function in this case. It will be a function of two variables, x1 feature and x2 feature. And you can plug in the value of x1 feature and x2 feature for any random tumor data point, and it will hand you over the, or it will output you the discriminant score. And based on that discriminant score, you can perform the classification. One last important question is that how the linear discriminant analysis calculations will work out in this case, and how linear discriminant analysis in this case is acting as a dimensionality reduction scheme. And that's pretty simple, guys, because in this case, our data is two-dimensional. That means for any data point, we have two values, x1 feature value and x2 feature value. But guys, the minute we plug in these values inside our discriminant function, then it gives us an output, a single discriminant score, which is a scalar quantity. So guys, you can see that the minute you are inserting your two-dimensional data inside the discriminant function, it is giving you output only a single dimensional quantity, and that is called the discriminant score. So it means that your two-dimensional data is getting transformed into a one-dimensional data in the form of a discriminant score. So guys, in this way, a kind of dimensionality reduction is happening. And that is how, guys, in this case, linear discriminant analysis is acting as a kind of a dimensionality reduction scheme. Okay, so guys, I hope that you guys might have got this whole concept of linear discriminant analysis, or the concept of performing classification in the case of 2D data, and your intuition or intuitive understanding regarding how classification is being performed on different data points has become even more clear. Okay, so that's it for this lecture, guys. Thank you.